This is Chapter 14, Physics, Lecture 2, and all of our problems today are going to come from page 469. So this is the middle lecture of 3 lectures. So a couple of review concepts going back to Chapter 8. With the conservation of energy, we have total energy is equal to potential energy plus kinetic energy. So with electric potential energy, you know that you can get that change of potential energy with Q delta V. Okay, we learned that last lecture. Kinetic energy uses the same equation it did all the way back in Chapter 8, 1/2 mv squared. All right, so if potential energy goes down, kinetic energy must go up, and vice versa to maintain energy conservation. So if you look at 14.5, it says a 6.5 coulomb charged particle is placed 1.4 meters from a 3.4 coulomb stationary charge. So this is our fixed charge right here. How fast will the particle be traveling when it's 2.5 meters away? Okay, so they're like charges, they'll repel, and the total distance after they travel, all right, would be a total distance of 2.5 meters. We're wanting to know how fast is that 6.5 coulomb charge going after it's been pushed out to 2.5 meters. Okay, well, first of all, let's get what we can get. We know we can get our initial voltage. That's going to be K, big Q, over R. So that's 9 times 10 to the 9th times 3.4 coulombs, which is a huge charge, lightning bolt, divided by 1.4 meters. All right, and that is 2.19 times 10 to the 10th volts. Now our final voltage, the only thing that changes is the denominator. So 9 times 10 to the 9th times 3.4 coulombs. It's just the fixed charge. And it moves out to 2.5 meters. So of course it's going to go down, and it goes down to 1.224 times 10 to the 10th volts. All right, so in order to get velocity, we're going to need to get kinetic energy, and in order to get kinetic energy, we need to get potential energy. To get potential energy, we know that change in potential energy is Q delta V. We know Q, it's 6.5 coulombs, so let's get delta V. That's the final voltage minus the initial voltage. So 1.224 times 10 to the 10th minus 2.19 times 10 to the 10th. And then your calculator will tell you that that is negative 9.62 times 10 to the 9th volts. Well, now we can get change of potential energy. That's Q delta V. Little q is 6.5 coulombs. Doesn't mean it's a little charge, it means it's the moving charge. Times negative 9.62 times 10 to the 9th volts. That's what we just calculated. All right, place that into your calculator and you will get negative 6.25 times 10 to the 10th joules. So that's our potential energy decreased by that much. So our change in kinetic energy, since energy must be conserved, it's a positive 6.25 times 10 to the 10th joules. And we can set that equal to 1/2 mv squared. All right, so our velocity is going to be, solving for velocity, it's going to be the square root of 6.25 times 10 to the 10th joules divided by 1/2 times the mass, and looking back at the problem, the mass is 42.3 kilograms. All right, if you place that into your calculator properly, you'll get 5.44 times 10 to the fourth. All right, that's a 4. 10 to the fourth meters per second. Oh, I'm so sorry, excuse me. The flowers are blooming. Okay, one way you'll know that maybe you accidentally forget to take the square root, if you get a number bigger than 3 times 10 to the 8th, nothing can go faster than that. That's the speed of light, so you know that maybe you forgot to take the square root at the end of it. So go ahead and pause the video if you need to. I'm going to erase this. And let's look at 14.6. So that one says a negative 7.1 millicoulomb charged particle is placed 65 centimeters from a 5.2 millicoulomb stationary charge. If the particle starts at rest, how fast will it be moving after it has traveled 15 centimeters? Okay, let's put the initial diagram here. So we have a 5.2 millicoulomb plus 5.2 millicoulomb. That's our fixed charge. And it is 65 centimeters from a negative 7.1 charge. All right, and so this is our fixed charge. Stationary charge held in place. All right, if the particle starts at rest, how fast will it be moving after it's traveled 15 centimeters? So their opposite charges, positive and negative, they are going to attract. So this is going to move 15 centimeters towards the fixed charge. So the final distance between the two will be 65 minus 15, or 50 centimeters. All right, so let's get the initial voltage. That's K, big Q, over R. So that's 9 times 10 to the 9th times 5.2 times 10 to the minus 3. And we were initially at 0.65 meters. So that initial voltage is 7.2 times 10 to the 7th volts. Our final voltage, KQ over R, 9 times 10 to the 9th. The numerator is the same, 5.2 times 10 to the minus 3. But our final distance is 0.5 meters. All right, so that is 9.36 times 10 to the 7th. So we know we need to get the change in voltage. V final minus V initial. 9.36 times 10 to the 7th minus 7.2 times 10 to the 7th. That's 2.16 times 10 to the 7th volts. Okay, so now we can get the change in potential energy. That's Q delta V. Little q is negative 7.1 times 10 to the minus 3. All right, that's this guy. Times 2.16 times 10 to the 7th volts. Your calculator will hopefully tell you that's negative 1.53 times 10 to the 5th. Joules. So potential energy went down, kinetic energy must go up. And that's going to be a positive 1.53 times 10 to the 5th joules. We're going to set that equal to 1/2 mv squared. The mass is 1.1 kilograms. So velocity is the square root 1.53 times 10 to the 5th joules over 1/2 times 1.1 kilograms. All right, and in your calculator, that'll give you 528 meters per second. All right, if you need to, pause the video so you can catch up. All right, and I will work the third and final problem of this lecture. This next one takes a little more space. So it says an 8.8 millicoulomb charged particle is shot with an initial velocity of 255 meters per second towards a 4.5 millicoulomb stationary charge. If the particle starts out 1.2 meters from the stationary charge, how close will it come to the charge before turning around and moving away? Okay, if you're given velocity first, you can calculate kinetic energy. So we know that's 1/2 mv squared. So that'll be 1/2. The mass is 3.5 kilograms. And then velocity is 255 meters per second. Don't forget to square that. And when you do, you'll get 1.14 times 10 to the 5th joules. But this next part is really important. The particles are both positively charged. They will repel. So if a positive charge is shot towards another positive charge, it's going to resist and want to turn around and go the other way. So kinetic energy is getting slower. All right, velocity is reducing. That means kinetic energy must be negative. Okay? It's slowing down. Kinetic energy is negative. Therefore, the potential energy is positive. 1.14 times 10 to the 5th joules. We know that this is equal to Q delta V. All right? Little q is 8.8 millicoulombs. Excuse me, that'd be coulombs. 8.8 times 10 to the 3rd coulombs. All right, and then we need to get delta V. Okay, so delta V, 1.14 times 10 to the 5th joules over 8.8 times 10 to the 3rd coulombs. So delta V is 3.38 times 10 to the 7th, no, excuse me, that's not right, 1.29 times 10 to the 7th joules. Now, in order to get that final distance, I need to get the final voltage because that's KQ over R, and I need R. So I could get final voltage if I can get initial voltage, which I do have the information to get. All right, the initial voltage is the fixed charge, is K, 9 times 10 to the 9th, times the fixed charge, which is 4.5 millicoulombs. So 4.5 times 10 to the minus 3 coulombs. And then the initial distance is 1.2 meters. All right, so our initial voltage is 3.38 times 10 to the 7th volts. All right, if the change in voltage is the final voltage minus the initial voltage, and I need final voltage, all right, I need this guy, we can solve for final voltage. it's going to be delta V plus the initial voltage. All right, so we're just going to have to add these two, delta V, initial voltage. All right, if you add those two together, right, you will get 4.67 times 10 to the 7th volts. Again, that's just change in voltage plus the initial voltage. Now I can, if our final voltage is K times the fixed charge big Q over R, solving for R, you just switch these two, right? R is equal to K times big Q over the final voltage. So R is equal to 9 times 10 to the 9th. Right, big Q is right up here, 4.5 times 10 to the minus 3. And our final voltage right here, we just calculated that as 4.67 times 10 to the 7th volts. All right, that was a lot of work, but we get 0.87 meters. Okay, so based on this lecture, what homework can you do? Well, you can do review question number 7. And you can do practice problems 4 through 7. Right, so that's on page 485. So give those a try, and we will finish up this chapter with the next lecture on capacitors.